Okay, so let's make completely an example of diagonalization. So we need to find eigenvalues. This is actually a matrix that I gave earlier, but let's do the computation here. Eigenvalues, eigenvector. If we have enough eigenvectors, we put them in the matrix P, and then we can write P, D. I will assume that you know how to compute P minus 1. So let's find the eigenvalues. So you can pause and do the calculations. That would be very nice. And then come back to check if that's all right. If you really don't know how to do, well, just follow the calculations. So eigenvalues, I need characteristic equation, determinant of A minus lambda I. So I must compute determinant of 3 minus lambda, 0 minus 1, 2, 4 minus lambda, 2, -1, 0, 3 minus lambda. Okay, so let's compute this determinant. I'm going to expand according to, well, I'm choosing the first row because it's going to, because it has a 0 inside, so it's going to make it easier. So let me just write the details. So it's going to be plus 3 minus lambda times the determinant of these two subcolumns. So that's just 4 minus lambda, 2, 0, 3 minus lambda. Then I would have 0 times the determinant of, well, those two columns. Well, it's just going to be 0, okay. And then I would have plus -1, so -1 times the determinant of those ones, so which makes 2, 4 minus lambda, -1, and 0. So now let me expand that. I've got 3 minus lambda times 4 minus lambda times 3 minus lambda minus 0 minus 1 times 2 times 0 minus, so I've got plus 1 times 4 minus lambda times -1. So minus in the end. I get minus 4 minus lambda. So although I've got another 3 polynomial, I can factor it. So either can get some nice factorization, either you would get an obvious root so that you can factor later. So, but we will practice that for the 3 polynomials. I know we don't have any direct formula to get the roots of another 3 polynomials, so there will always be a trick. Here I can factor both sides by, both terms by 4 minus lambda, and I've got 3 minus lambda square, which makes 9 plus lambda 2 minus 2 times 3, so 6 lambda minus 1, right? So this is 4 minus lambda times lambda 2 minus 6 lambda plus 8. So I need to find the roots of this one. The delta is 36 minus 4 times 8 is 32, that's 4. And my roots are going to be minus 6, so that's plus 6, plus or minus 2 over 2, which make 4 over 2, that's 2, and 8 over 2, that's 4. So I've got 4 as another root. All right, so that's 4 minus lambda times lambda minus 4 times lambda minus 2, which I can factor as minus 4 or minus lambda or minus lambda minus 4 to the square, lambda minus 2. So as we said earlier, we've got 4 eigenvalue of multiplicity 2 and 2 eigenvalue of multiplicity 1. Okay, so now we need to find eigenvectors. So eigenvectors, let's find with the 2 for 2. Okay, so I need to rewrite. I'm looking for the null space of a minus 2 times I. Okay, this is what I'm looking for. So I need to write a minus 2 times I. So that's my matrix. Let me rewrite this quickly here. 3, 0, -1, 2, 4, 2, and 0, -1, 0, 3. So minus 2i, so I put minus 2 on the diagonal, so that's just going to be 3 minus 2, that's 1, 0, negative 1, 2, 2, 2, and I get negative 1, negative 1, 0, and 3 minus 2, that's 1. Okay, so what does that give me? All right, so that's giving me all right, so if I reduce that, well, I can, so I'm looking for x, y, z such that this is equal to 0. So let's put it under the usual form. So I get 1, 0, negative 1. Row 2 minus 2 times row 1, that's just going to be 0. That gives me 2. That gives me 4. And now I get row 3 minus 2 times my plus row 1, that's just 0, 0. Okay, so I can even go further in the simplification. I can get 0, negative 1, and I can get 0, 1, 2. Okay, so I've got one free variable, which is z, and I've got two linked variables, two dependent variables. Okay, so this one is free, and the pivot ones are going to be the dependent. Okay, so if I choose z is equal to 1, what do I get? I get y is equal to, so what actually I'm solving is going to be this equals to 0, 0, 0. So first row gives me x minus z is equal to 0, so x is equal to z. And second row gives me y plus 2z is equal to 0, so y is equal to negative 2z. Right? So my free variable, let's put z is equal to 1, then y is equal to negative 2, and x is equal to 1. So that's it. All my solutions are going to be collinear to that vector. My eigenvector is 1, negative 2, 1, or anything collinear to this one. Of course, you don't have a single eigenvector. Anything, you could choose anything. I could get minus 1, 2, and minus 1. I could get 2, minus 4, 2. That would be still the eigenvectors. The idea is that they just span exactly the same space, right? So that's my eigenvector associated to the eigenvalue 2. Now, eigenvector associated to eigenvalue 4. Okay, so I must compute the null space of A minus 4 times I. And so if I write this matrix, it's just going to be, I had 3 minus 4, so negative 1, 0, negative 1. And then I get 2. 4 minus 4, that's 0, and then I get 2 also. And finally, I get negative 1, 0, 3 minus 4, that's negative 1. So I've got 3 times the same row, which is something that I hoped for. Wasn't sure I would find it, but I did hope for. Why? Because the reduced row echelon matrix of this is just going to be 1, 0, 1. Okay, one single row, right? So I've got only one, I would have two free variables and one dependent because I've got only one pivot. Okay, so let's see what we have. So that means I will be able to find two linearly independent eigenvectors. So free variables are the z and the y, okay, and x is equal to negative z, right? Because this is solving xyz is equal to 0, 0, 0. You see that the value of y has absolutely no influence, but I must have that x plus z is equal to 0, so x is equal to negative z. So we've got two possible eigenvectors. So I do choice y is equal to 1, z is equal to 0, and then y is equal to 0, z is equal to 1. And that's giving me for 1, 0, 0 for the first one. And then second one would give me negative 1, 0, negative plus 1. Right? So my eigenspace is spanned by this one. Okay, so finally, what can I do? My D matrix is going to be, so I've got 4, which is a double eigenvalue, and 2, which is a single eigenvalue. Right? So, yeah, that's it. Right? So that's my D matrix. By convention, we usually put the higher eigenvalues first, but this is really a convention. Sometimes people do the contrary. I think in economy they put the lower eigenvalues first, but most of the time we will put the highest eigenvalues first. We will explain this later. Okay, what would be my P matrix? In my P matrix, I get the eigenvectors in the same order as the eigenvalue comes. For my two eigenvectors, sorry, that was the eigenspace associated to 4. For my two eigenvectors associated to 4, I put them in any order that I want. The thing is that if you compute p minus 1, it's just going to depend on the p you chose, all right? Your p must correspond to the d, but then the p minus 1 depends on the p. So if you choose this eigenvector first or the other one, it really doesn't matter as long as they both correspond to the eigenvalue 4, all right? So I get maybe it would be easier to invert if I put the second one first. So let's put this one 0 plus 1, but really it doesn't matter. Okay, and 0 1 0. Okay, these are the eigenvectors that correspond to my eigenvalue 4, and then I want the eigenvector corresponding to eigenvalue 2, which was this one 1 negative 2 1. Okay, so 1, negative 2, 1. This is my P matrix. And well, you can check, well, you should compute the P minus 1. We won't do this. I assume you know how to do that. And I've got that A is P times D times P minus 1. Okay, and you can always check that this is correct by doing again the computation, right?